Hello friends, now we prove what is the tangential velocity. So we know that the velocity component along the tangent is called tangential velocity. Velocity component along the tangent is called tangential velocity. Here we find out expression for velocity in intrinsic form. So first we know that what is the intrinsic form. If the equation of a curve is in the term of s and psi, where s is the arc length and psi is the angle made by the tangent with the x-axis. So that equation is called intrinsic form of equation. So what is the intrinsic form? Intrinsic form means that equation represent in s and psi, where s is the arc length and psi is the angle made by the tangent with the x-axis. So here we find tangential velocity, or we can say that expression for velocity in intrinsic form. So first we suppose that let a particle moves on a curve APQ. Let a particle move on a curve APQ. Suppose that this is the particle which moves on this curve APQ. Suppose that this a particle here moves on this curve APQ. Let A be the fixed point here. A is the fixed point and arc AP, this is equal to smallest, and arc AQ, this is equal to S plus del S. Here A is the fixed point. We suppose that this arc AP, length of this arc AP be S, and length of this arc AQ be S plus del S. Now we find out the arc length of PQ. So arc length of PQ is equal to arc length of AQ minus arc length of AP. So arc length of AQ is here S plus del S, and arc length of AP is S here. So S is cancelled out. So this is del S. So we can see that arc PQ, this is equal to del S. Now we suppose that at time t, the particle is at point Q, at point P, and at time t plus del t, the particle is at point Q. Here we suppose that at time t, the particle is at point P, and at time t plus del t, the particle is at point Q. Now we draw tangent here. Suppose this is y-axis and this is x-axis here. This is x-axis and this is y-axis, and here this is the origin. Now we draw here the tangents at P point and here Q point also. Suppose that PT, this is the tangent at P point, and QT dash, this is the tangent at Q point. Let's draw tangents PT and QT dash at P and Q. Let us suppose that these tangents intersect at L point. Suppose that this tangent intersect at L point. Let us suppose that this tangent at P makes angle psi with x-axis, and tangent at Q makes an angle psi plus del psi with x-axis. Here we suppose that the tangent at P point makes an angle psi with x-axis. Tangent at P makes angle psi with x-axis and tangent at Q makes angle psi plus del psi with x-axis. You can see here PT the tangent at P point which makes angle psi with x-axis, and here QT dash is also the tangent at Q point which makes angle psi plus del psi with x-axis. Now we find here the angle this TLT dash. We know that angle TLT dash this is equal to psi plus del psi minus psi. So this is equal to del psi. You can see here this angle is del psi here. Now we can see this is del psi, so angle this, suppose this point is R here, this angle is del psi also, because this is the vertically opposite angle. This angle and this angle TLT dash and angle QLR, these are the vertically opposite angles, so this is also angle del psi. We can write here this angle is here, this is del psi angle. Now we draw a perpendicular from Q point on QM. Suppose QM is the perpendicular drawn from Q point on this tangent PLR. Draw a perpendicular QM from Q on tangent PLR. You can see here we draw a perpendicular from Q point on the tangent PLR. Now we find here tangential velocity. So we know that velocity that is the rate of change of displacement. So we find here tangential velocity. So this can be written as limit till t tends to 0, and here we find the displacement along the tangent in time del t. Here we find out tangential velocity, so we write here displacement along tangent in time del t divided by del t. So when we find displacement along the tangent, rate of change of displacement along the tangent in time del t, we get the tangential velocity. So we find here displacement along tangent PLR in time del t divided by del t. So displacement along tangent PLR in time del t is here. This is LM. This is when you can see here in time del t the displacement along the tangent is PM here. You can see here since this Q point and P point are very close, so this triangle PMQ is as a right angle triangle. So in this triangle, first we find here PM. So first we find here, you can see cos del psi. So cos del psi is equal to base upon hypotenuse. Here we find out in triangle PQM. Cos del psi is equal to base upon hypotenuse. So base is PM here and hypotenuse is PQ, called PQ. You can see here this is PQ, or we write here this chord PQ. You can see here there when we find the cosine of this angle del psi, we find here angle QPM. Sorry, this is angle QPM. Angle QPM. Here in this triangle PQM, we find this angle QPM, cosine of this angle QPM. So cosine of angle QPM, this is equal to base upon hypotenuse. So base is here PM and hypotenuse is called PQ. Because P and Q points are very close, so this triangle PQM becomes a right angle triangle. So in this right angle triangle, we find cosine of angle QPM. So cos QPM is equal to base, this is PM, upon hypotenuse, this is called PQ. So in place of PM, we write here, chord PQ cos angle QPM divided by delta. So we find here tangential velocity. Tangential velocity is equal to limit del t tends to 0, displacement along tangent in time del t divided by del t, and displacement along tangent, here the tangent is PLR. So displacement along PLR in time del t. In time del t, how much the displacement is? Here the displacement in time del t along the tangent PLR is PM upon del t. And we can see here, since this point P and Q are very close, so triangle QPM, this is right angle triangle, so PQ behaves as hypotenuse. So we find here cosine of angle QPM. So cos angle QPM is equal to base, this is PM upon hypotenuse is called PQ. So this here we find PM is equal to chord PQ multiplied by cos angle QPM. Now we can write this. We can write this limit del t tends to 0, and here we write chord PQ divided by del S multiplied by del S upon del t multiplied by cos angle QPM. You can see here in the numerator and denominator we multiply del S. Here we multiply del S in the numerator and denominator. You can see from the figure, when del t tends to 0, that means Q point approaches to P point. When angle when Q point approaches to P point, so angle QPM this becomes 0. When del t tends to 0, so Q point approaches to P point. When Q point approaches to P point, so angle QPM tends to 0. You can see here when del t tends to 0, then Q approaches P point, then angle QPM tends to 0. So cos angle QPM this is equal to 1, and when this del t tends to 0, chord PQ and del S both are equal to 1. So taking limit here, when we take limit, this becomes 1 here, and this convert ds by dt, and here this is also 1. When del t tends to 0, Q point approaches to P point, so angle QPM tends to 0, so cosine of angle QPM is equal to 1. So this becomes 1 when we take limit del S upon del t, this is ds upon dt, and chord PQ this becomes 1. Limit of this chord PQ upon del S is equal to 1. So this is ds upon dt, and this can be written as S dot. So here we can see this is the tangential velocity. So tangential velocity is ds upon dt. Thank you.